record. Excellent. Hello, everyone. Is everyone in the meeting? It looks good. Okay. We are going to get started. Can you hear me? Yes, it looks like people can. It looks like my video is on. This is good. All right. James, I'm going to ask you to watch the waiting room and make sure you keep admitting people. That would be great. Okay. So welcome everyone heavens. To our bulk power system training. This is our first event in our spring bulk power system training series on large loads. Today's event, as you can see on the screen, is advancements in resource adequacy assessments to consider transmission, large loads, and flexibility. So before we hear from our speakers, I'm just going to give you a little bit of background on NARUC, the National Association of Regulatory Utility Commissioners, and the Center for Partnerships and Innovation, which is a part of NARUC. So NARUC started way back in 1889. We are a nonprofit membership association for state PUCs in 50 states, the District of Columbia, the Virgin Islands, and Puerto Rico. Our mission is to serve in the public interest by improving the quality and effectiveness of public utility regulation, and this training series is right in line with that goal. So I work for NARUC in the Center for Partnerships and Innovation, or CPI. CPI is the group that provides technical assistance to our members, and we do that in a variety of ways like this training today, webinars and convening work groups. We give sincere thanks to the Department of Energy for funding this and our many other efforts. So I just want to say that NARUC has been offering these virtual training sessions on bulk power systems since 2021, and these resources have been developed by NARUC, by the National Association of State Energy Officials, the National Association of State Utility Consumer Advocates, the U.S. Department of Energy, and we have had a number of partners in doing this, and the Energy Systems Integration Group, ESIG, is one of those partners. We're really glad that they're here with us today. You can access more than 12 different former recordings and presentations on bulk power system issues. I'm going to drop a website link in the chat after I stop talking, but you can also just search the NARUC website for bulk power system and it will take you right there. And it is, there's really a lot of good stuff in there. There's like, what's a generation queue? How does all of this work? So there's some really great stuff. Also on the website, you can register for the next two sessions in this large load training series. And those next two sessions are going to cover forecasting large loads and harnessing flexibility to inform resource and transmission planning on April 16th. And then on April 30th, we're going to cover processing large load interconnection requests. And of course, when I say we, I mean the team from ESIG. So today's training, again, we're going to start with how planners connect transmission to resource adequacy assessments. We're going to hear from MISO about how they evaluate the resource adequacy value of transmission. And then in the second part of our 2.5-hour training today, we're going to dig into the flexibility of large loads and how that can be incorporated into resource adequacy planning. And then the training is going to end with a look at the near-term winter resource adequacy challenges here in the Pacific Northwest, which is actually where I'm located. So I'm going to pass this over to James Okulo, who's an engineer with the Energy Systems Integration Group, and he's going to go through the rest of the agenda and kick us off. Thank you so much, James.
Thanks, Deborah. Thank you, everyone. We really enjoy these trainings that we do with NARUC. We've done a few of these over the years, and like Deborah said, you have access to all of that material. And we think we're an incredibly important group of people to talk to, and that's why we come back again and again and come with some old friends and some new friends. So a lot of the people that you see today should be familiar with you to you. So ESIG, we're a member-driven organization that's really focused on surfacing, framing, identifying those technical challenges that we see on the system, and then coming up with solutions. We also look at the opportunities that are in the system that perhaps are not being fully tapped, and we'll talk about some of that, I think, over the course of this training. So we have a number of materials that we put out through our webinars, through blogs, through reports and white papers, and through our workshops. We had one just 2 weeks ago, and we'll be having another one in the summer. And all that information you can find on our website. We also do a number of task forces, which a few of you have been a part of. And one that is relevant for today's conversation is on our large loads task force. Um, so, like Deborah said, this is a series of trainings that we'll be doing. The first one looking at resource adequacy, and resource adequacy, thinking about that as you have enough resources to serve your load, right? And that's changing a bit, right? What we mean by a resource, what does transmission now do, both as a resource and how does it fit in that mix? And of course, on the load and demand side, right, we're seeing changes there on the load itself, but the load perhaps being a resource, and that's all material that we'll be covering today. Just briefly, the Large Load Task Force has been working on several areas, right? Everything from forecasting, rate impacts, markets operations, and of course, today's topic on resource adequacy. We have already published a number of papers in the last few weeks, and you can find all those at our website. There's a link at the bottom there. And then finally, agenda, like Deborah went over very well. The first half or so, we'll be talking about transmission. Then we'll talk about large loads, and then Elaine will bring it home talking about RA kind of broadly in the Pacific Northwest, but with some large loads baked in there as well. So without taking up more time, I'll pass this over to you, Kevin, if you want to kick us off. I will say for Q&A, please put your questions in the Q&A. We will then be asking those questions directly to the speakers on your behalf. Okay, thank you. Thanks, Kevin.
Great, thanks, James. And I assume that I should be sharing my screen here.
That's right.
Okay, 1 second, let me make sure. Okay, appreciate the introduction, James. Looking forward to the opportunity today. The goal of this presentation is to share some general thoughts about how we look at the effects that transmission has on resource adequacy planning. Now, obviously, transmission doesn't produce any of its own generation, so how does it contribute directly to reliability? How does it help balance the load and generation problem that we're concerned with in the resource adequacy space? I'm going to try to introduce a handful of heuristics that can help folks to get a sense of how transmission affects resource adequacy, even though that may not be directly embedded in these slides. These slides are a refresh or an intro into some work that we did for ERCOT as we started to look at internal transmission constraints within the system. So the work that we did in ERCOT, historically, we have always assumed that this ERCOT system is essentially a copper sheet. So any generation produced anywhere inside of the ERCOT system is fully deliverable to load anywhere within the ERCOT system as well. During peak conditions, you are mostly able to deliver generation from ERCOT. Most of the congestion doesn't necessarily happen at those critical hours, but there are periods where during reliability events, congestion occurs as well. Part of that's due to the way the system is operated, that you may relax some constraints during critical reliability events where typically you are committing and dispatching resources to maintain security constrained economic dispatch, which means that we have evaluated all N-1 conditions and we're able to deliver around those. So in the resource adequacy space, we're looking at these more extreme scenarios, extreme conditions. And so that assumption has generally held for most resource adequacy work done around the country, to be frank, that generation within this larger area is more or less deliverable to load within that same area. Oh, excuse me. But as we start to look at larger systems, ultimately there is an impact of those internal transmission constraints. We need to understand the impact that those have. So the first kind of finding or heuristic I want to leave folks with is the concept that the smaller the zone is, the less reliability contribution that energy limited non-dispatchable resources are expected to bring. So think about a really small, few hundred megawatt system, islanded system. If they have battery capacity, if I lose one conventional generator, I may need days and days of generation in order to provide reliability. And so a 4-hour battery is unlikely to provide full reliability contribution. So the smaller the system, those energy limited, non-dispatchable, including renewables and others, are going to end up more constrained, not be able to provide as much reliability. So as we start to look at smaller systems, we will start to see some of the reliability contributions of those resources to become less valuable. Now, that also applies to conventional resources as well. If I have a really small system, what's the ELCC if I have one generator to serve this one islanded load? Well, I probably need to carry a 200% or 300% reserve margin in order to serve that load. So the ELCC of that resource is going to decline. So the more we consider the internal constraints, the lower the reliability contribution and the higher the PRM that's required to maintain reliability. For ERCOT, so historically we've looked at it as an island. When we start to take into account those constraints, both of those effects are going to show up, that existing resources, energy limited, non-dispatchable, and even conventional, will be expected to provide slightly lower or potentially lower ELCCs, and the planning reserve margin that you need to keep would need to increase. Now, all that depends. The trade-off between PRM and ELCC can get pretty complicated, but that's generally the idea that I would keep in mind. ELCC will decline, PRM will go up. So more constraints, it's harder to meet reliability. So the task that we had for ERCOT was to break up the system into a number of zones to be able to assess what are the impacts of those internal constraints. ERCOT has identified a number of critical flow gates, and so they passed that information to us, and we used our Terra model, which is a nodal transmission reliability model that looks at the impact of constraints on the transmission system. So we took Terra and we looked at the impact. So for a critical summer day, critical winter day, what impact does each bus have on those flow gates? The next step, once we've taken that clustering task to group these zones, the next step is to perform transfer limit analysis to understand what are the constraints from zone to zone, and then what are the aggregated constraints of total ability to import power into that zone, total ability to export power from that zone. And then the next step is to take all that information, run serve them to understand the change in reliability for 2026 when you go from that copper sheet analysis where everything's fully deliverable to the clustered representation. Here's a visual of the results of that analysis. So you can see that we have 8 zones shown here. So again, since we're using Terra to identify this, it's really the electrical proximity of each of these nodes rather than kind of geographical or by ownership. But this represents kind of where we expect to have transmission constraints. We've grouped all these nodes in such a way that it should give us the best representation in a zonal model that you expect the actual transmission system to have on reliability. Once we have those 8 zones, next step, as I mentioned, was transfer limit analysis. So we will proportionally scale up generation in the sending zone, down generation in the receiving zone to identify how much swing do we have before we run into a binding constraint. So we're doing this looking primarily at overloads. And so where do we hit an overload on a particular path? And at that point, once we have a binding mon-con pair, we're going to identify that as the transfer limit. Whatever the aggregated transfers are in that scenario will define the transfer limit that we put into serve them. So if between zone A and zone B, we could scale up generation by 4,000 megawatts in one zone and scale down generation by 4,000 megawatts in another zone. We have a net flow of 4,000 megawatts going across that path. That 4,000 megawatts determines our transfer limit. We also do an aggregated transfer calculation where we scale up generation in one zone and then scale down generation in all the other zones. That will tell us our export limit. And then the same idea, but scale down in the receiving zone and scale up in the external world and see how much we can change before we hit those transfer limits. Now, this is still I would categorize this as research grade. It's, as you'll start to see in the results that I show, there are a lot of ways that the system changes during emergencies in terms of the flexibility that you have to call demand response, to call voltage reduction, other emergency operating procedures that we can employ that will affect our ability to deliver power across the zone. So as I start to talk through these results, keep that in mind that when we jump from 0.2 LOLE to 3 LOLE, it doesn't necessarily translate to direct needs that we think that the ERCOT particular zones are going to need. But here are the results of the transfer limit analysis. So we have the clusters, the 8 clusters. We calculated the transfer limits for the summer and for the winter. So we have different limits in the sending and receiving directions. The aggregated constraints are defined for each one of the zones here inside these bubbles. And this information ultimately helps us to identify kind of where we expect to see some binding constraints. What do the results look like? So from our copper sheet scenario, so we assume that generation is fully deliverable across all of ERCOT. We ended up at a reliability level of 0.21. This doesn't benchmark directly to public results that you've probably seen, but it's in the ballpark that we expect in the near term. There's likely some risk to being able to meet the 1 day in 10 standard. So 0.21 means we expect 2 events in 10 years rather than, or 2 days of loss of load rather than 1 day in 10 years of lost load. When we impose the path limits, so those discrete path limits between zone A and zone B, between zone B and zone C, reliability declines, but it's a modest decline. So we go from 0.21 to 0.228 in cluster 1. So some of the zones that were close to that already, we don't expect there to be much of an impact. So this is essentially 1 event in 100 years, additional reliability events that we expect due to that transfer constraint. Clusters 2 through 5, and then cluster 13, all of their events are concentrated at the same time. So this, since they are all the same, 2, 3, 4, 5 can transfer enough power, but they are not able to get power from 6, 9, and 1 as needed in order to satisfy reliability events. So there are some constraints between zones 1, 6, and 9 to get to the other zones. So it just shows in general that we are adding 1 or 2 events in 100 years due to these path limits only. The real impact to reliability is when we took into account the aggregated constraints as well. So the net import that a zone might have, the net export limits that a zone might have, we're considering these simultaneously. So this is layered on top of each other. We take the path limits on top of the copper sheet, and then we do the path limits plus the aggregated constraints together to understand kind of aggregate reliability. With both of these constrained, we see that cluster 4, and cluster 4 was a Western Texas zone that has a lot of wind, has a lot of solar. It has a large import limit, but if you have a big wind lull and overnight hours, we started to see some reliability events in cluster 4 where we could not import more than, let's see if I have it here. Cluster 4, it's like more than 10,000 megawatts into cluster 4. Same thing in cluster 9. So the aggregated constraints have a bigger impact. This nets out that a lot of these events now are occurring at different times, and our aggregated is 6 events per year. Now, the work that we're doing with ERCOT this year is going to further explore, what type of remedial actions might you employ. So in this case, we are still respecting the N-1 requirement, but during emergencies, some of those constraints can be relaxed. trying to just give some visual for how this transpires. You can see essentially which zones have surplus in all hours versus which zones have a shortfall. You notice in the prior slide that all zones had some loss of load. So even if the zone had its own internal surplus, we are still sharing some of those shortfalls to the extent that the transmission constraints are not binding. So if one zone is short and there's transfer capability, it will help even to the extent that it may shed load inside a zone that had surplus. There are a number of zones that from their own load resource balance needed to import significant amount of capacity in a number of hours. So zone 4, this western zone, more than half the hours in a year, it was short on its own load resource balance. So it has to import a lot of generation. Again, zooming into the effects for zone 4, you can see kind of the aggregated constraint actually here was a little over 7,000 megawatts. So with the 7,000 megawatt transfer limit across the entire year, and this is just summer hours, so we get 5,700 hours in March through October, I think is how we categorize this period. In almost every hour, we have enough excess or import capability from the neighbors to satisfy our load resource balance. But there are a handful of hours, and that's all that it takes. You just need to violate this in 1 or 2 hours a year in order to be worse than industry standard reliability. What does an actual event look like? And I mentioned that it's kind of driven by the nature of the portfolio in zone 4. So we have a lot of wind, we have a lot of solar. And during the daytime, we never have a shortfall. We're able to export power most of the time from zone 4. But overnight, we have a wind lull on this day. We're only getting a few hundred megawatts of wind, no solar, obviously, overnight. We are purchasing as much as we can. So we're at the transfer limit as far as purchases. And then the rest of the generation, so we are still dispatching from our storage, from other resources, but we have this unserved energy kind of in this overnight hour period. And these are the types of effects that we ultimately want to understand. If there is a binding constraint in zone 4, that could affect the reliability contribution that solar may bring. If because of this, all the events occur in overnight hours, what's the reliability contribution of solar expected to be? Well, it's probably going to be 0. Same thing for wind. If it's driven by wind lulls, the output during these critical hours is load, so wind will have a lower value. Then if we considered what is the reliability contribution of this resource if there are no internal constraints across all of Texas? So again, back to my initial point, when you start to consider these constraints, it's going to lower the ELCC of particular resource classes. I'm not going to be able to cover all the material in this slide. Hopefully, I've kind of given some perspective of how this works. So when we run the Servum simulations, we can look at individual snapshot hours so we can see for this particular hour that cluster 1 is transferring all that it can to cluster 4. We still have a reliability event in cluster 4. But the transfers across all the zones, Servum is trying to economically and reliably transfer power as efficiently as possible. Just briefly, mitigation opportunities. So lots of things that you can do to try to solve these transfer constraints. We can re-optimize commitment. Outage planning may affect that. If I have scheduled outages during shoulder periods, that could affect the ability to import into a zone. So these are the kinds of things that we're testing this year to understand what flexibility do we have to resolve those constraints. Relax N-1 security constraints. So during an emergency, are you going to shed load preemptively in order to respect the N-1 constraint? Well, probably not. So we need to think about those kinds of things. And ultimately, this kind of work helps us to calculate zone-specific ELCCs, zone-specific, what's the right type of resource to add to a specific zone. Deborah, I think I'm going to pause there. I think I've covered most of the material that I expected to cover today. Do we have any questions?
Yeah, currently there are no open questions either in the chat or in the Q&A. So if folks would like to try raising your hands, I think we can allow you to unmute and ask a question if you wish.
While we're waiting on those, I will just kind of offer kind of what's the next step in this type of analysis? Where do we want to go with this? So obviously with looking at nodal reliability analysis, it's challenging to simulate the number of cases that we do in a typical resource adequacy study that's on a zonal basis. So for a study like this for ERCOT, you're running 40 weather years, 5 load forecast years, 100 generator outage profiles. You may end up with hundreds of millions or billions of hourly simulations that you perform in the zonal model. The idea is you're not going to be able to run that in a nodal model typically in an efficient way. So we use SERVM as a scenario generation engine to identify those hours where we have constraints. And then we pass those scenarios over to Terra to do a deeper dive and see what remedial opportunities you have to resolve those constraints or to understand if there are truly binding constraints on the system.
Thank you, Kevin. Here is one question from Finlay Salter. When working with ERCOT, how did you determine what actual zone clusters would be delineated?
Yeah, great question. I'm going to go back to slide. So ERCOT gave us the list of their critical flow gates. So we have a definition of the flow gates, and so we're monitoring those flow gates. And when we run analysis in Terra, we can see what is the sensitivity of each node on that particular flow gate. And nodes that have similar impact on the flow gate were grouped together. So it's essentially calculating how changing of the dispatch at one particular node affects power on that flow gate, power flow on that flow gate. And so that allows us to kind of group nodes by electrical proximity. All right, any other questions, Deborah?
Yes, actually, there is another question from Andrew Willard. What impact, if any, do distribution utility load transfer capabilities and load shedding for flexibility under a node impact these studies? That's a big one.
Yeah, good question. This may be one that other folks will want to take on as well when we start to look at large loads, because a lot of those questions of the fungibility of resources, I'm going to consider demand response as a resource, can affect the reliability contribution of other resources. So if you're able to shed load selectively in a particular zone, maybe on an economic basis, it's not considered a reliability event. You have some capabilities to do that on an economic basis, perhaps as part of some kind of program. Those resources are generally, they have some type of limitation on them. They can only be called a certain number of times per year, hours per year. If I think about the rest of my portfolio, if I have other energy limited resources, you have to understand that there's some impact of calling a demand response resource that you could have used an energy storage resource for. So if I have two different programs, one's a DR program that has 4 hours a day of call rights, and then I've got batteries that have 4 hours of duration, that those resources are going to be competing for the same reliability contribution as each other. And so planning has to be comprehensive, centralized. You need to understand the impact of all kind of portfolio changes, remedial opportunities that you have when you're looking at reliability in aggregate.
I don't see any more questions. And so, James, I will turn it over to you.
All right, because we have just a minute left here before we switch over to Armando. Kevin, going back to the first question, when we're talking about the electrical zones, right, and how those may or may not line up very well with utility boundaries or states or different jurisdictions, I think you made the case that we do want to include transmission constraints and foam zones when we're thinking about RA. have you given any thought, particularly for this group, right? How you navigate the electrical boundaries from other boundaries?
Yeah, it's certainly challenging because if utilities span state lines, if utilities the primary kind of transfer constraint is not on the threshold of their load zone, it certainly makes it challenging for accreditation questions, for assessments, so forth. So it's certainly a policy question that's pretty difficult, really difficult to answer. Most of the work that we have done has primarily been on the technical side, to be honest, that it is really about understanding kind of the electrical contribution that a resource has. But there may be opportunities kind of for smaller zonal definitions from the electrical proximity standpoint versus kind of larger zones from a geographical weather zone. So like, ERCOT has, I think it's 5 weather zones that they typically represent this system in. But from an accreditation standpoint, I would certainly think there's value in aligning the accreditation scheme with an electrical proximity based zonal mapping.
Mhm. All right, thank you. And I think you absolutely hit it right on the head, right? This is difficult, right? When you start thinking about those boundaries and how to think about it. And yes, there's a technical answer. We need to marry that and reconcile it with some of the other considerations. So thank you, Kevin. Thank you so much for that
Yeah,
wonderful presentation.
thanks,
We
folks.
will pass it on to Armando. And I realize we did not give full intros of all the speakers. And I'm going to request the NERUC folks that when they are posting this text and the materials to post the bios as well online. All right, Armando, we'll turn it over to you.
All right. Thank you, James. And quick check. Can you see slides? They coming through
Yes, we do.
Yes. Okay. Perfect.
Looks great.
Thank you, Deborah, and good afternoon, everyone. And my name is Armando Figueroa. I'm with MISO Strategic Assessments Team, senior engineer. And what I want to talk about today is the methodology that we use as part of the long-range transmission planning, Tranche 2.1 portfolio. In particular, the one that we developed for the avoided capacity cost benefit metrics. So what I'm going to do here is talk from beginning to end how we develop the assumptions that are needed to calculate the metric, how we develop the methodology, and then how we report the results and how it fits within the full benefit metrics that set of metrics that are part of the business case. I'll talk about the whole process as well. That's not directly related to the technical aspect only, but also just stakeholders engagement. So I'll start here. I think this is where it all starts with MISO's 7-step process. So this is a process that we use for transmission planning purposes, and this is to plan again for long-term transmission projects and portfolios. And it all starts with the definition of the scenarios and what we call the futures, which is nothing else that 20-year outlook of generation and load forecast that our members are planning for. So we take that information and then we identify that then the needs part comes in and identify potential transmission issues that might arise 10 and 20 years from now based on that underlying portfolio of generation and then load forecast. And then we, in collaboration with stakeholders, we start analyzing and proposing transmission projects that will solve those issues from multiple angles, not only the reliability, but also from the economic point of view, from the resource adequacy point of view, from all these different lenses that make what we call the multi-value portfolio or proposition. So once we evaluate all those transmission, we call transmission candidates or options, then we recommend the preferred solutions. Right? We start with a list of 100 transmission lines options, and we narrowed down to the top 10, 15, more or less, depending on the portfolio, that are then passed to the next and final stage, which involves cost allocation, benefit analysis, etc. You'll see that this seven-step process is well aligned with FERC Order 1920. There are a few things that we are adjusting to make it more one-on-one to the order, but the concept and the structure is well aligned with the FERC order. So I'm going to focus on steps 6 and 7, which are the ones that cover the benefit metrics portion and the avoided capacity cost. And as I said, I'm gonna describe from beginning to end how we calculate the metric, how we did it for the last set of the tranches. So I mentioned briefly the ACC, we call it ACC metric, or avoided capacity cost, is part of a bigger list of metrics that we use in the LRTP business case and benefit analysis. We start with as I said, with the definition of the futures, and then we define 2 of them to make sure we have a broader range of potential paths or futures that could develop based again on members' plans and load forecasting. For the particular methodologies that we develop in the last set of the tranches, we leverage methodology from the ESEC. One of the ESEC reports that talk about methodologies for the different benefits, and the one about capacity, avoided capacity costs. We align pretty well with that methodology. Uses probabilistic methods, and I'm going to talk about that shortly. But the metric is part of a broader set of metrics, and I'll talk about that later on, how the results compare of this metric relative to the other metrics that we have. But this is the range of metrics that we calculate, right, or the set of metrics that we calculate for valuing transmission at the regional level, and for tranche 2.1 in this case. So it all starts, as I said, with the resource forecasting, right? So where and when resources are going to be sited and injected or connected into the electric system. So we start with an initial model build, resource expansion, and we have assumptions here about fuel prices, about capital cost of new generation units. We have retirement information. We include the load forecast and policies related to renewables, decarbonization, etc., emissions. So all that is part of that first step or first bucket that we execute before doing any of the other transmission planning activities. So that's done at the regional level. Then we translate that at the nodal level, specific buses and nodes in the system. And there's a full process, again, collaboration with stakeholders on where those new generators are going to be located at, where we're going to allocate load, where units are going to be retired, and when as well. So all those decisions are made in those first 2 buckets. And then we have an energy, we call energy adequacy assessment as well. And now it's we're refreshing these features. There's a new component here called resource adequacy, which is conceptually is similar, where we look at 8760 hours of the year and see if there are any hours where the portfolio doesn't have enough generation at the regional level to supply load. In the first step of the expansion, we use limited information from a production cost point of view. It's a very simplified production cost that is used in an expansion. So that's why we have that calibration at the end to make sure that all hours in a year are adequate. So once we finish that, then we have a generation portfolio load assumptions that are ready for the next step in the process, which involves evaluating both the reliability and economic needs of the system with what we call the system intact. So there are projects from the transmission side that are planned for the next 5 and some of them 10 years as well. But the 20-year out model, it's mostly whatever it's in the 10-year model gets carried over to those later years. So when we simulate the system with the new generation portfolio and the new load forecast, we start to see issues, right? We start to see congestion. We start to see voltage and thermal violation in our reliability modeling and simulations. And that's the part where we start doing the engineering transmission planning activities to solve those issues and propose projects that will solve those issues and enable the members plans that we identify and aggregated in step one. This is a more detailed slide with all the different cases that we developed. We run a 10-year out and a 20-year out power flow models that include peak load conditions, summer peak, winter peak, and shoulder months as well. So we have a light load and average load, and a few of them have high renewable generation scenarios as well. But that's what we use for what we call the reliability planning work stream of the LRTP process, or the 7-step MTEP process. It's important. I didn't include a slide about the economic planning portion or work stream of this framework because this is the one that we use in the ACC benefit, and want to be able to connect the dots here with the actual process that is upstream of the benefit calculation. That it's the very last process that we that we do in that LRTP planning. So I'm going to focus on the 2042 because that's the year that the model that we evaluate for the ACC calculation. Might be asking why not a 2032 or even every 5 year, or every 2 year, or even every year. One of them is time. So if we have 10 years to do it, then we could do every year, right, and evaluate all possible combinations. But we're time constrained. Also, the complexity of developing these models, and most importantly, what we want to evaluate is when the entire portfolio is in service, what's the value that it can provide. So we need to make some assumptions about phase in, etc. But that's the question that we're asking here ourselves when we evaluate benefits of long-term transmission, is when the whole portfolio is in, what's the value? Because that's the one that's going to set the longer term benefits for the rest of the planning horizon. So I'm going to focus on that bucket, on the core model potential solutions, which is an extended version of the core model that includes the portfolio that we are evaluating, that we're calculating the benefits for. Added a few details here around the type of contingencies that we assume in those power flow models, based on TPLRI, all the NERC standards. We follow those standards for development of these models. Monitor all the facilities, including some of the interties with neighbors. But that's the essence of the reliability. So this sets the transmission, or part of the transmission topology that we use as an assumption to the ACC calculation. So now we have two. We have the generation portfolio on the load forecast, and the transmission topology that we need to calculate the ACC benefit in a probabilistic framework. And I'll very briefly touch on this one because, and I think Kevin did a great job at that, articulating, right, the difference between the regional and zonal, and importance of the higher granularity, and how it's integrated into a probabilistic framework. We typically do resource adequacy on a copper sheet basis, where we have a huge bubble, right, where there are no constraints between areas, zones, or nodes. We'll call the copper sheet scenario. For LRTP, Tranche 2, and the benefit analysis, we MICE already have zones we call local resource zones that are approximately based on states boundaries. We have 10 of them at MISO for LRTP because it's a north and south focused portfolio. We evaluated the first seven that are in the north central area. But this is where we combine the information from the first few steps in the 7-step process with probabilistic methods. So we're combining methodologies from resource adequacy / loss of load expectation with the transmission planning process in the 7-step process. Question is, how do we do that? And more formally, we define the avoided capacity cost metric as one that reflects the capital cost savings from increased transmission capability that is provided by the portfolio. And it also enable access to resources over a wider MISO footprint. So we combine probabilistic modeling that has been historically been used for resource adequacy with the transmission processes that we have at MISO. We've been using for now three regional transmission portfolios, including the MVPs, Tranche 1 and Tranche 2.1. So how do we measure the benefits? There are two pieces here. One is the quantification of the benefits in megawatts units, and then the monetization of that benefit in dollars. And I'll start with the first one. How do we get the megawatt benefit? We start with a case that doesn't have the effects of the portfolio. So it's a case that includes transmission, we call transfer constraints, but without the transmission portfolio that we're evaluating, right? And then, so we run a simulation and we drive the system to criteria. Then we add the portfolio, the reliability increases, right? Because you have more capacity in those pipes to share resources during types of needs, not only during the 3 critical periods that are normally analyzed in part flow. We look at 8760, different weather years, different samples as well from an outage and generation outage point of view. And then we do the same thing. We run the analysis and we drive the system to criteria. The benefit we calculated as the difference between the adjustments that are needed to bring the case without the portfolio to criteria and the case with the portfolios. So it's very similar to the concept of the effective load carrying capability or ELCC. It's measuring the value or capacity value of transmission by combining these two processes, if you will. Little bit of a long flow diagram here, but it I think fleshes out the entire process for quantifying the benefit in megawatt units. I'll talk about the monetization shortly here, but starting from left to right, we begin with our futures development. Then we develop a loss of load expectation model that includes the multiple weather years, outage. It's run on an A760 basis. And then we branch out. Now we have a single model that then we divide into two. One that will include transfer limits between LRCs that don't capture LRTP, and another one that do capture LRTP. So one is going to have more transmission capability than the other one, right? Then we tune both or adjust both to the one they intend, LOE standard. And then what we do is we calculate requirements for both of them, planning reserve requirements at the MISO-wide level. The difference in the requirements between the two, that's the quantity that we are that we measure as the benefit in megawatts or percentage of the portfolio, right? So it's a way of isolating the benefit of an element or a combination of elements, in this case of a portfolio, transmission portfolio, from the rest of the system, and measuring benefits of that particular group of elements in the system. So once we finish that, we have a megawatt quantity. Then the question becomes, how do you monetize that? And there are different options here. And as part of the 1920 task force, EC task force, we're discussing the different methodologies, different ways you can do this. Straightforward way of doing it is to apply a cost of re-entry, right, to that value, and assume that it's a combustion turbine or another technology. But that's one way of measuring the monetary value of those megawatts. Another way of doing it, it's the one that we adopted here in the LRTP Tranche 2.1, is that we run an optimization to figure out what's the optimal mix that would meet that benefit, right? So let's say we have a 10 gigawatt of benefit that transmission provides. What is the composition of those 10,000 megawatts that in MISO we call it UCAP terms, right? In firm capacity terms. It could be all of them be met by a CT, right, or a combined cycle. But we led an optimization that was informed by the previous expansion planning model, figure out what the optimal mix. And we found that it's a combination of solar, wind, storage, and also gas that made up that benefit. So we run that optimization and then found the 20-year NPV in dollar terms, all reflected to a 2024 current year. So that's how we split it, the calculation into the benefit in megawatts and the benefit in economic value. One question is, how do you implement this in an optimization? It's very similar to a resource expansion planning tool, full resource expansion planning tool. What we ended up doing was we assumed that the benefit increased linearly from year 2032, which is the year 10, which is where we expect projects to start to get built, all the way through 2042, which is the final year in the planning horizon, the 20-year out. So we assume that it's linear relationship. You can do more granular analysis if time allows to fine tune those, but we found that this was a good and adequate assumption to not increase benefits or develop benefits that were too high and not too conservative either. So that was the assumption that we ended up doing or making for this monetization portion of the benefit that included that additional part of the optimization, figure out the composition of that benefit. The next few slides, I'll conclude some of the results that we developed as part of this effort. So this graph shows benefits in millions of dollars with different discount rates. We want to have a range here in the benefit in the business case and benefit analysis. Everything is referred to 2024 dollars floor amounts, and you see two bars here, four actually. The two in greens are the 20-year, 4-year NPV, and then the blue ones are the 20-year present value totals. And I'll wrap up with this one here. At the beginning, I told you that this was ACC was part of a bigger set, right, of benefits. And in this diagram, I show you all the benefits that were calculated, including a few of them related to extreme event or extreme weathers, losses, transmission investment, your typical production cost, outage costs, and decarbonization. So those are the ones that made up the full stack of total benefits. ACC, and there's a small portion here of reduced losses as well as part of that bucket. The methodology was slightly different, but the monetization part was the same. But here you can see that it's the third highest category of benefits in the whole list of benefit metrics. So at the end, we found the portfolio tranche 2.1 benefit to cost range from 1.8 to 3.5, which includes the ACC benefit. So with that, I'll stop here and see if there are any questions. But again, thank you for the opportunity to present, and looking forward to the questions. Pass back to you, James or Deborah.
Great, thanks, Armando. Deborah, do we see any questions for Armando?
Not yet.
Okay. We'll give a moment if someone wants to come off mute for a question for Armando from ISO. All right. Thank you, Armando. And all the speakers' information is, I think, attached at the very end of their presentations. And we realize 30 minutes is not a lot of time, but you have full access to them outside of this set window. So thank you so much, Armando. And I appreciate the 1-2 punch from you and Kevin. Kevin talking about the need for a realistic representation of your system, especially as the system is changing, as resources are showing up in different places, as loads are showing up in different places. You want the transmission to be represented. And of course, he then laid the foundation for what mitigations could be, and you've filled that in. But yes, transmission can be a huge mitigating factor when you know where the resources are going, and you can avoid some of that capacity build because you are allowing more transfer capability between regions. So thank you so much, Armando. All right, we're going to have a small change in our program. Instead of Aaron going, we'll have Jeff Bladen from Veris talk about what does load flexibility in practice actually look like. So the first two presentations were on resource adequacy and transmission. We are transitioning into large loads and load flexibility. So Jeff, if you are there and ready, if you have your slides and want to share them, you can do that. Or perfect, wonderful. We see that. Turn it over to you, Jeff.
Great, and thank you for accommodating my schedule. And it's good to see you all here today, and look forward to talking to you a little bit about the other side of the equation. What does it look like in practice to actually support resource adequacy with load flexibility, in particular in this case? And we've been hearing so much over the last few years about the growth of data center demand, in particular, these very large data center campuses that really dwarf anything that we've seen in the electric industry previously. And so the opportunity to potentially have significant amounts of demand flexibility from these, at least some of these, is a real innovation, and it is something that Veris in particular has been working on. There's others doing some as well. Just as by way of background, again, my name is Jeff Bladen. I serve as head of energy and policy at Veris. Previously served as head of the global energy team at Meta, and then before that, spent the bulk of my career across two RTOs, PJM and MISO, in operational and market design leadership roles. So just very quickly, what is Veris? The Veris was stood up about 3 years ago to really reimagine the data center as a grid asset. And this is not unique to Veris, but we are one of the first that are out there talking about what it looks like in practice to actually deploy the kind of flexibility at scale that's possible. So ultimately, it looks like transforming IT loads, or what would otherwise be static IT loads, into a dispatchable grid responsive resource. We do it with a new integrated power flow platform that looks like a combination of software and infrastructure innovations at the data centers. So that allows us to do dynamic load balancing and actually support the grid as a shock absorber. We're supporting it also with a transition to large scale utility scale batteries in lieu of diesel generation. So the batteries provide a synchronized grid forming asset that can be deployed to flex demand up and down. And again, who is Veris? It's some of the most experienced folks from the technology world coming together to try and build something new. Lots of focus on how to support the grid as a primary element of the mission. We won't do too much of the ad, but if you have questions about what we're doing, certainly feel free to follow up. So when you think about large load flexibility, there's this matrix of potential options to think about. The flexibility categories look like really three categories. One is pure curtailment, where the demand just goes away for some period of time, at least from the grid's perspective. The second is time shifting, where the demand is shifted away from periods of grid stress and into periods of low stress or moderate stress, such that it's better for the grid to balance it that way. And then the last category is location shifting, and this would be where if you have a fleet of, in this case, data centers that are serving customers, the potential to shift the load or the demand, the compute demand from one location to another, um, uh, in with grids relative grid stress of the different locations in mind when you do that shifting. So an example might be moving video transcoding or streaming activities from a data center on one coast of the US to the other, timed with when demand is highest for different parts of the country. This last category is somewhat more limited because data center capacity is generally very constrained, and so most capacity is consumed already. So shifting locations is very difficult because there's not slack capacity sitting in one location that you can shift demand to, the vast majority of the time. And then across those three flexibility categories, there's two primary mechanisms that you would use to actually execute the types of flexibility. The first is software-based, and the second is facility-based. I'll sort of run through the software-based. And so in the case of pure curtailment, software-based would be essentially not doing something that you might otherwise do. Even if it's delaying when you're doing it, it's essentially a missed opportunity. So an example would be not running an AI training model at a time when you'd want to run it. And uh, Another example would be reducing maybe the sample rate of data that is streaming. So you get lower resolution video. It might go from 4K to traditional high def, as an example. Those are essentially pure curtailments of the amount of compute, and that can potentially reduce the amount of electricity demand. On a time shifting basis using software, that can look like scheduling demand. So choosing to schedule training runs or other kinds of activities. Maybe it's backing up uh, 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 images or video in some form or fashion, but scheduling them at a time that is away from when the grid would be most stressed. On a facility or infrastructure basis across those categories, you have the first category of curtailment looks like an import reduction. That's what that means is taking less power off the grid when the grid is stressed. And so that's usually going to be delivered by some kind of on-site power resource. So it could be power generation like gas or some kind of other fuel-based resource that turns on during those periods, and that essentially reduces the amount of demand that's being consumed off the grid during that period. The second one, time shifting, would look like, but still asset backed, would look like potentially battery energy storage or some kind of mechanism to store energy in some other fashion, such that you could then release it um, uh, during times of grid stress and then refill it or recharge it during times of low grid stress. So those are really the general categories when you think about flexibility for large loads. So what Verus is doing and what makes us different is that, as I said earlier, we're using battery energy storage to deliver the second category of asset-backed flexibility. So essentially allows our operations to charge the batteries when the grid is not stressed and discharge them when the grid is stressed. In practice, the batteries for us serve multiple other purposes, which is part of why you see somebody like Verus doing this and others not really focused on this approach. But the batteries can generally be a very effective backup tool, which is why they're able to displace diesel generation in our case. Um, and just as by way of reference, there's a few other things that differentiate our data centers, including more efficient cooling systems that consume dramatically less water, and then, as I mentioned, the ability to use the battery energy storage to support the grid when it's stressed in multiple ways. In our case, we're designing our flexible response capabilities around the NERC reserve standard. So everything from uh, primary reserves, which is sometimes called capacity, and it's what MISO capacity market that we were just talking about procures. But it also runs the gamut to other sorts of contingency management solutions that are sometimes called ancillary services, from a few seconds response to 10-minute or 30-minute response. It's worth noting that all of these solutions where you are shifting demand away from the periods of grid stress and shifting them into periods of low grid stress will have an outsized effect on helping keep general rates in check for other customers. And the main reason for that is that what drives rate increases generally, even if there's a desire to allocate costs directly to customers that may be driving those rate increases, it's still true that most other customers across the grid, setting aside the large load ones, are still mostly when you add new loads, we're driving up the peak of the system. And so as we drive up the peak of the system, we have to pay for those new generators. We have to pay for that additional transmission infrastructure. What large flexible loads can do is to spread the cost of that new infrastructure that other customers are really driving, and actually pay for some of it by using it during low stress periods, so off peak periods. And that's done because of the flexibility. And so the effect of having flexible large loads on the system is outsized in terms of this rate dampening or cost increase effect that you'd otherwise see from traditional load growth of homes or businesses. And that's an important element of thinking about how to shape policy as we go forward, is that while adding large loads generally will have some of this effect, adding large flexible loads has this outsized effect on keeping rates more affordable. And to be clear, this is not a new understanding of demand response or flexibility. It's simply an amplified version of it, because these new large customers have the potential to be even more of an impact through demand response. So what you see on this chart is really just a visual description of this rate dampening effect that flexibility can have. That by shifting by adding new demand, but keeping that new demand away from the peaks, it's essentially consuming slack peak capacity that's being driven by other kinds of load growth. And that then in turn means that the new capacity is getting the costs are being spread across not just the existing customer base who are driving demand growth with other kinds of electrification, whether it's electric vehicles or adding air conditioning or the like, but also it allows for that new load growth, that new capacity or infrastructure growth to be paid down in part by these new large customers that are flexible, that are avoiding contributing to that peak growth. And so as it notes here, it allows you to avoid infrastructure to a degree, or at least mitigate the amount of new infrastructure and more broadly spread the cost of new infrastructure. That creates some downward pressure on rates. It also provides some new reliability tools for grid operators like MISO to deploy during times of grid stress. So it's in many respects a win-win. I'll note from my time in control rooms at PJM at MISO, there really is no more reliable way to manage grid stress than to reduce demand if you have a high degree of control over it. There is always some risk when you try to dispatch generators, particularly ones that are offline. To try and get them online there's risk attached to it. And then even online generators, when they attempt to ramp up above their eco max, there's some risk of running them for any period of time above eco max. And so having demand that can flex down is more than likely the most reliable way of managing grid stress for those kinds of periods. Again, assuming you feel very confident in the source of the demand response. And for the vast majority of demand response, that's true. I'll mention just in passing, in case you want to learn more about some of the work that's gone into developing these new kinds of data centers. There's a couple of research papers that have been published by what's now called the National Lab of the Rockies. It was previously called the National Renewable Energy Lab, that talks about a 70 megawatt hardware in the loop testing regime that answered many of the key questions about whether a large flexible load like we're talking about can help support reliability in the ways that the grids need. Both Xcel Energy and MISO supported in the development of the testing protocols that were then run on this simulation platform hosted at NREL. And I think the link is in this deck, but if it's not, we can certainly send it around. And I'll make one pitch as you think about where to focus and how to unlock large flexible loads. There are some key challenges in the current regulatory construct. In particular, we don't really have a concept of a class of customers that are large and flexible. We may have in limited instances industrial interruptible tariffs, but those are not always fit for purpose of this sort, in that we're talking about maybe at a scale that was not contemplated. Um, uh, the other challenge is that our traditional processes for interconnecting customers don't necessarily line up with studies, don't necessarily produce studies that take flexibility into account. And so instead of a study saying we've got this new large customer, but they'll be off during the times of grid stress, the studies will say, we know they're flexible, but we're going to ignore that, and we're going to tell you what infrastructure needs to get built, despite the fact that this customer can commit to not being on during those times of grid stress. And so the impact of that is to drive new infrastructure build that might not be necessary, and it also reduces the amount of money that can be paid towards existing infrastructure as a result, and using the effect I was describing earlier. We also today don't prioritize beneficial loads of this sort. We treat them exactly the same as we treat any other kind of load, despite the fact that they would have an outsized impact on helping keep rates in check for all customers. And so that's something to consider. And then to the extent that there are questions about how to design tariffs or riders or other kinds of rate structures that unlock the value of flexibility, it's important to look first at the NERC reliability standards. Those are a great benchmark for how to think about what flexibility has value to the grid for reliability and for other customers to drive affordability. And I guess I will stop and take questions. I stuck to my 15 minutes.
Nicely done, Jeff. So there are several questions from Heather Moline. The first one is, are your batteries available for grid use and dispatch, or only to the data center itself? Have you experimented with configuring them in different ways at all?
The short answer is yes, they're available to the grid to dispatch pretty much throughout the year, and pretty much on an unlimited number of dispatches during the course of the year. At our first two hyperscale sites, one of them happens to be in MISO. Our expectation is to provide all of or nearly all of the capacity requirements using demand response. And so we would be following MISO dispatch in order to do that. At another site, we would be working with a vertically integrated investor-owned utility to support N-1 contingency management, again, at their dispatch.
Okay. Thank you. The next one is also from Heather Moline. So in the Northwest, reliability events are largely driven by multi-day cold snaps. And are your batteries typically like 4-hour batteries? What have you got there?
Yes, they are in base design for our batteries. And based on our analysis, even in the Pacific Northwest, those multi-day cold snaps don't stress the grid for more than a few hours at a time. At the most extreme stresses when you would dispatch an emergency resource of the sort we're talking about. Um, where you have the need for thousands of hours of dispatch, it's really required to build new sources of power generation. Those locations in the U.S. tend to be few and far between at this point. It's not unexpected. It would be unexpected to get to a place where emergency resources would be needed more than a few hundred hours a year, though.
Thank you. And then finally, do you have the kind of data you need to enable large load flexibility? Is it readily available? And do you rely on feeder level data, or is it, and of course you're more focused on a single site, but yeah.
Uh, I'm not quite sure what data is being referred to. I think we understand the grid well enough to know that in most locations, our ability to flex 4 hours at a time, roughly any time of year for, days in a row if needed, with some recharge time during off-peak periods between. Um, we generally can get pretty good data from the Nuclear Regulatory Commission about the reliability of the high voltage system and what the probable dispatches are for emergencies. I'm not sure if that's the data that was being referred to. I think what isn't available today is where a flexible load might be able to interconnect faster, but that others are waiting in line because they need upgrades. And nor is there a process today to enable that, where we can allow customers that are capable of connecting to the grid as it is to do that instead of waiting in line behind those that need major upgrades and might take years to get those upgrades in place. Essentially, our process is connect everybody who, sort of first in, first out. If you request to connect, even if you're driving 5 years worth of upgrades, everybody behind you has to wait for your upgrades to be done before they can connect, even if they don't need those upgrades.
Thank you. That is an interesting point. So then there's one more question from Finlay Salter. Is your best strategy used to reduce the peak demand scheduled in the electric service agreement that the utility actually plans for? Or are you writing in an assumption of curtailability in the electric service agreement, like 50 hours of curtailment per year? This, I think, goes to rates, how you pay or how
Yeah, I
you're
mean,
compensated.
I think it so far has varied from utility to utility. Our expectation is to have a minimum build demand that we will easily exceed every month, mainly because our design is a much more productive one. So where a traditional data center might be around 65% load factor, our data centers tend to be up into the low 90s on load factor. Again, that has to do with the nature of how flexibility works, where we're using more energy when the grid is not stressed, but those few hundred hours a year when the grid is very stressed, we're using a lot less energy. So that has the effect of raising load factors, and it turns into the ability to pay more towards the existing system and help reduce rates in that regard. But in general, in terms of rates, we would expect to connect at if it's a vertically integrated utility, we would expect to use the appropriate large industrial tariffs, and pay those rates as they are, pay for all of the infrastructure upgrades that are required for our site. Usually it's a substation and a short line extension. And then to the extent that it's not vertically integrated, where maybe it's a wires only utility, we would expect to bring our own capacity requirements and then still pay for all of the energy we consume, as well as all of the upgrades, like a substation and a line extension.
Thank you. James?
All right, yeah, we have, I think, a minute for another question here, Jeff, before you have to drop. So as we're thinking about the changing system, right? Like every load or generator that we add into the system maybe changes the RA risk somewhat differently. It might not be worse, right? But it's different. So we've talked about solar moving the net peak into later into the day, right? It might be a shorter period and perhaps more acute, but it's different, right? And we have to contend with that. And storage, perhaps, shrinking it, if you add more and more, 4-hour storage, then you flatten the risk profile, and then you need a different kind of resource. Again, not worse, but different. As we're thinking about large loads that have a fairly, high load factor, and then you're adding, batteries on top of that to charge them, perhaps, is that then looking like, 100 megawatts plus, 10 megawatts or whatever it is at off-peak period in such a way that it is changing the risk profile in a way that we're not familiar with? Have you looked into that, and what does that look like for RA planning and mitigation?
I mean, I think you're right that we should be paying attention to the potential changes. I can't say that we've looked at that specifically. What I can tell you is that there are very few that are pursuing the magnitude of flexibility that Verus is. And so the vast majority of new large loads that are connecting are still of the more, I would describe them as legacy sort, with not as high a load factor. And so they're essentially driving peak much more than somebody like Verus is. Whereas we're going to drive off-peak energy consumption, they'll drive on-peak capacity requirements. And so what we're able to do is to help mitigate some of the costs that go along with that new increase in peak. The other thing that we're seeing across all rate classes is significant electrification, which also tends to be peak driven. Obviously, we're trying our best to get people to charge their cars at night instead of at 5:30 when they get home, but I think we've only had some limited success with that. The same holds true with lots of businesses electrifying every various parts of their businesses, and all of those things, is for good or for ill, are driving peak much more than they're driving base load. And so, at least for some time to come, it looks like the ability to use storage to help manage making the system more efficient is a good path forward. I think the difference with what we're doing is that the storage comes to the grid essentially for free instead of at cost, because we're building it for other purposes and we're able to deploy it to serve the grid. There is essentially zero capital cost for deploying our flexibility, whereas there is obviously all the capital costs associated with grid interconnected storage.
All right, thank you. Thank you so much, Jeff. Thank you for sticking to your 15-minute and having time to answer 5 questions. Thank you so much for the presentation. We appreciate your time.
Thank you.
All right. Next, we will have Aaron from TELUS talk about some of the work that they have done, including some of the work that they led for ESIG on the large load task force looking at resource adequacy. Aaron, I'll turn it over to you now. Thank you.
Great. Thank you, James. And thanks for having me. I'm Aaron Schwartz. I'm a senior engineer at Telos Energy. And today I'll be talking about integrating large loads and flexibility into resource adequacy planning. So I think Jeff laid a really useful foundation for jumping into discussion of what flexibility can look like, what some of those different mechanisms for flexibility are. Um, and in this presentation, we're going to dive a little bit more deeply into what it might actually look like to really building this into planning. And I think that bounces really well off of one of Jeff's recommendations is, really establishing better pathways for studying and ultimately valuing flexibility within utility studies and operational realities. So I think we are already pretty well oriented with the challenge at hand, which is that a surge of data center driven load growth is reshaping electric power systems planning. Um, really, really dramatic projections up to 12% of total US electricity consumption by 2028, according to Lawrence Berkeley National Lab. And I think one of the key things, takeaways from this slide is that there is a lot of capital at stake here, 200 to 600 billion in electric sector capital investments projected worldwide by 2030, at stake in the planning decisions that regulatory staff will be supporting and helping making over the coming years. So we're at a really critical juncture, and making sure that we get this right is essential. And I think Jeff also alluded to this, but I think an important assumption to keep in mind when thinking about these projections and assumptions is that traditionally, the assumption has been that data centers or other large loads have been more or less inflexible. And so I think it's important to try and shift that perspective and think about, will we need to build as much new capital investment? Will this cost as much? And I think what we're seeing in some of our research is that the answer may be not as much. We'll get into that. So for the next couple of slides, I want to sort of take just a pause and speak a little bit more high level than just talking about flexibility and thinking about what we might be thinking as far as effective pathways for integrating large loads more broadly into utility planning. So the first suggestion that I'll offer are really thinking about ways of ensuring that we're not planning for overbuilt capacity due to uncertain large load forecasts as part of utility planning processes such as IRP. Scenario analysis is a really like a cornerstone of the IRP process in thinking, in allowing us to really explore uncertainty. And I would argue that large loads are one of the foremost uncertainties that we are navigating today. So I'm not arguing that large loads aren't here and that they're coming, but I do want to emphasize that there's still a lot of uncertainty on the timing and magnitude of that, and especially region by region and jurisdiction by jurisdiction. There's uncertainty associated with the underlying technology, potential efficiencies that we may see going forward in both software as well as data center and chip design. We're already starting to see certain challenges associated with permitting, siting, as well as potential supply chain challenges that can affect what actually materializes in any jurisdiction. So if there's one sort of like key takeaway from this presentation, and you'll hear me kind of say this over and over again, it's use IRP, use planning as an opportunity to isolate the impacts. And the impacts I'm referring to on this slide are specifically what the capacity build out might look like driven by large loads. And so we suggest as part of planning to use a no large load scenario as a reference point, as a way to isolate the incremental capacity impacts that large loads may be driving within an IRP or resource portfolio. So these figures come from expert testimony that Telos Energy provided as part of the Georgia Power 2025 IRP proceeding, in which we looked at Georgia Power's base load forecast, and it's for all loads. The majority of the growth was driven by large loads, but we then adjusted some assumptions to develop a 50% forecast, as well as a no large loads forecast. The idea here being not to saying that these are more likely or less likely, but just that by having these reference points, we're able to look at scenarios that can then isolate the specific capacity additions that are being driven by that large load capacity. And that's what we see on this figure up on the right. And so, we see large loads really driving an increased capacity need, driving, for example, a greater need for gas CCs in those portfolios. And I think this gives us a useful opportunities to take a step back and say, how can we preserve optionality, provided that there's this uncertainty in these forecasts? What are the types of investment pathways that are consistent across? Maybe across investment pathways, there's a more near-term need for a certain type of resource, or maybe there's options that we can better leverage the existing fleet of resources to give us some time as we assess how these forecasts may change. And final bullet on the lower left, lower right here is there's an opportunity to utilize backup bids in resource procurement to adjust as the forecast changes. So in addition to isolating the incremental capacity needs from large loads, there's also an opportunity to isolate those incremental costs and use that information to ensure fair cost allocation. And I should have caveated in this discussion in the previous slide, these are under the assumption of these large loads coming online absent flexibility. So assuming they're 100% firm, that firm capacity needs to be met with capacity additions as needed to meet the planning reserve margin. As just mentioned in the previous presentation, and as we'll talk about later, once we start layering flexibility assumptions, the results may look very different as far as what the capacity needs, what the costs might be from these additions. So as in the previous slide, IRPs can and always should include a reference point without the addition of large loads. And this can serve as a counterfactual for what generation or transmission costs would be required of existing ratepayers to meet that additional load. And this can be really useful information for cost allocations as well as supporting rate negotiations. And I think this is a call to action as I see it of thinking about ways that we can better integrate or harmonize various proceedings. So for example, by conducting a capacity expansion analysis that helps us isolate these costs associated with new large loads, that could be really valuable information that could inform cost allocation or a rate case proceeding. And so I think finding ways to share information to make sure that there's awareness of what's going on, even ideally finding ways to harmonize or share assumptions can be really, really useful in making sure that the findings that we may have from one proceeding are able to translate to really maximize impact across all of the relevant proceedings that are dealing with load growth and large loads. And so final sort of high level opportunities before we dive into flexibility is using long-term contracts to determine which loads should be included in the forecast. Right now, queue shopping is pervasive, especially among today's data center loads and hyperscalers. And this is increasing the risk of overstating total data center demand when we look at these nationwide forecasts or RTO-wide interconnection queues, or excuse me, interconnection queues across regions. From the sort of hyperscaler or data center perspective, this helps preserve optionality. They're not sure where or when they'll be able to actually put steel in the ground. But from a planner's perspective, from a forecasting perspective, this makes things a lot more challenging. And you may have heard the term phantom loads. That's what this is referring to. So instead, IRPs should not just rely on queue requests as the primary input to the load forecast, but ideally be able to rely on long-term contracts and agreements that show upfront collateral already being placed to really have confidence in that load showing up. There's been a good deal of great work coming out on large load tariff designs and uh, principles for ratepayer protection. And I'll just share one of them here. On the right is Google's capacity commitment framework. So arguing that large load contracts should be non-discriminatory, that is applying to all loads above a certain size equally, that they should be sort of a long-term commitment so that we can be confident that they're going to show up and stick around. Minimum charges that are sort of a high function of what a total demand charge would be, so that regardless of how much power they're using during high demand periods, we know that they're going to be paying for what they're projected to be using. Next is upfront collateral, so ensuring that there's multiple years of upfront charges that can help really put that skin in the game. And finally, recognizing that things do change, making sure that there's flexible and transparent mechanisms for modifying whatever contracts are in place. So this is just one example of what some of these planning principles might look like. But I think the idea here is that we should be having these conversations. We should be thinking about what sort of skin in the game do these large loads have? How confident can we be that they will actually materialize? And that can help bring in additional confidence as we go through the planning exercise with the load forecasts that are being included. And it sounds like this is a right topic for the next NEAR training on forecasting large loads. And I imagine there's much more to be said then. So now zooming in to the role of flexibility, and why should we be thinking about flexibility from large loads? So number one, flexibility offers an opportunity to decrease total capacity needs. We can reduce supply side investments, and avoid having to put steel in the ground when there may be alternatives. We can better utilize existing behind the meter generation for capacity. Most data centers, most large loads are already providing backup capacity in cases like the various data centers actually coming with integrated systems that are part of that system that can be used. So being able to tap into flexibility as a way of better leveraging resources that are already being developed as part of the large load designs. Next is that flexibility is a key tool for maintaining resource adequacy during scarcity events. Really, as we've seen, demand response can and will continue to be a key tool that already can support the grid during times of grid stress, and large load flexibility on this greater magnitude is no exception. And finally, we continue to see that we are in a supply constrained environment. Backlogs for gas turbines, for example, high cost, large load flexibility offers an alternative. I do want to make one quick note that flexibility can refer to many different types of flexibility. And for the context of resource adequacy in this discussion, this is flexibility for avoiding capacity shortfalls during these sort of rare periods of grid stress. So this is not flexibility that would be required on a daily or weekly or even necessarily monthly basis, but rather reserved for these rare events that may occur only a couple of times a year. In contrast, you may hear about flexibility for energy or ancillary services markets. These would be more frequent, but this is a different sort of a different use case and different type of flexibility response than we're talking about here. Oops. So as James mentioned, we at Telos have been supporting ESIG in a forthcoming task force report from the Large Loads Task Force on large loads and resource adequacy. And one of the centerpieces of this new report that should be coming out soon is a practical 6-step framework for planning for flexibility. And the idea is that this is a framework that can be actively used by resource planners at utilities and ISOs in order to really directly integrate flexibility into IRP or capacity accreditation frameworks. And the key idea is that this offers a way to plan for flexibility upfront in the capacity procurement process. And I think it's important to point out that the way that we're thinking about flexibility from large loads is different than how we may have historically thought about, for example, incentivizing demand response from traditional commercial or industrial loads. I think one of the big distinctions here is that the value of compute from data centers is extremely high, in some cases exceeding the price caps of the wholesale energy markets. And so these traditional sort of dollar per megawatt hour incentives won't necessarily incentivize the type of flexibility response that we want to be able to support resource adequacy. Instead, though, if we're able to bring those incentives up front in the capacity procurement process and frame it in terms of avoided capacity investments, or I think most essentially accelerated interconnection timelines that can help large loads interconnect more quickly than they otherwise would need to if they needed to wait for network upgrades for new generation to come online. That's a really powerful incentives, thinking maybe in terms of dollars per megawatt, for example, that we think will be effective of actually incentivizing this type of flexibility application for RA. So what's in this framework? So I'll quickly go through this at a high level and then dive in to some of the steps 2 through 5, more detail on the next slide. But at the highest level, we first want to understand what's behind the specific loads. Is it a data center? And if it's a data center, is it an AI data center? Is it a crypto mining load? Is it hydrogen? These are going to have different characteristics that we're going to want to make sure that we represent within the modeling. Which brings us to step 2 of improving the large load data inputs. I'm going to hold off on this discussion. This is my last slide. But I think as an industry, there's a lot of work that needs to be done to make sure that planners have the data that they need in order to do this type of analysis. In step 3, we want to quantify the capacity requirements of large loads absent flexibility. So this is sort of the traditional way of planning where we run a capacity expansion model, for example, where we assume that all incremental large loads are inflexible, it's fully firm capacity, that we will need additional resources to meet whatever increases there are to the reserve margin requirement. In step 4, we take a step back and say, okay, what if these large loads can be flexible? How much capacity value does that flexibility offer? And so being able to quantify that through, for example, ELCCs. In step 5, we put these pieces together. We incorporate the capacity contributions of flexibility into our model. We can rerun it with flexibility as a capacity resource, and we can now recompute the costs, capacity, and emissions with flexibility now as a resource in our portfolio. And then finally is developing a regulatory framework that ensures resource adequacy. So this is making sure that these results can trickle into relevant contract negotiations, tariff design, or other incentives, such as I mentioned, being able to incentivize accelerated interconnection in exchange for flexibility. So just zooming into a specific study that Telos supported along with GridLab, for actually following this process in bringing data center flexibility into specific capacity expansion modeling based on NV Energy's 2024 IRP. So our first step was to prepare the load data. This involved isolating the specific contributions from the hourly load profile from the data centers. In the next step, step B, we ran the capacity expansion model without any data center flexibility, giving us a baseline portfolio. And as I mentioned at the start, I think, again, the keywords here are isolate the impact. This gives us a baseline so that we can do that in subsequent steps. In step C here, we performed a ELCC study where we found the capacity accreditation of flexibility across different configurations. So we assessed both 1 gigawatt and 2 gigawatts of flexibility, as well as different total uptimes across uptime guarantees across the data center fleet. So 99% uptime would mean that 99.9% of the annual energy expected from that large load based on the forecast in step A needed to be served, but that 0.1% we were able to flex. In step D, we put the pieces of the puzzle together. We incorporated these ELCCs into the capacity expansion modeling, allowing the model to select flexibility as a capacity resource that can count towards the reserve margin requirement. And we're able to get a new set of outputs, new set of capacity investments, new set of costs, and new total emissions across this matrix of ELCCs. The final output was being able to compare the results from step B and step D, and we're able to identify incremental capacity needs, avoided costs, and avoided emissions, essentially allowing us to value concretely what flexibility is able to offer as a capacity resource to support resource adequacy. So just diving in a little bit more specifically into these results, ultimately, we found that flexibility can provide substantial savings. So across these scenarios, that range from around $300 to $400 million net present value. What this looked like as far as the portfolio is that as we look from 2030 to 2050, we compared to the baseline without flexibility, there were fewer capacity resources, here that being fewer natural gas resources that serve that similar peak load reduction capacity need that flexibility was. And instead, the model was invested in a greater share of low-cost energy resources, such as solar and storage. I think one interesting finding that I'll point out on the right on this ELCC matrix is that we get a lot of bang for our buck from a fairly small amount of flexibility. So just as a rough translation, if we just consider 99.9% of hours, that would be about 8 hours, 9 hours per year. We're already getting a 67% ELCC in this 1 gigawatt case. If we increase that from 99, or rather we increase the amount of energy available to be flexed by reducing the uptime, annual uptime, that goes up to 86%. And so really just emphasizing from leveraging flexibility for a small number of hours per year, we are able to see a real system benefit here. So my final slide really just highlights the fact that we do have a long way to go, I think, as an industry to get where we want and frankly need to be to really be able to integrate flexibility upfront in planning processes. And that requires more and better data. So there's a range of data that we need, ranging from sort of most basically, how big are the large loads that we're considering, to incorporating uncertainty through a load forecast range. I think most critical, I'll go about halfway down this table, are these hourly characteristics for functionally allowing us to model flexibility in resource adequacy assessments, in capacity expansion modeling. We really want to have these 8760 chronological hourly loads, and ideally disaggregated by individual load types. Fortunately, NV Energy did have this data for their 2024 IRP, and I hope other utilities will follow suit and provide that of disaggregated hourly load-specific data. Other data includes weather dependence. As we know, weather and weather dependence is a key part of resource adequacy assessments, and the specific weather dependence of large loads compared to underlying commercial, residential, industrial loads might look different. So really being able to tease out those differences. as well as understanding the specific resource configurations that may be behind the meter, whether that's on-site battery generation, whether those are backup diesel generators. The configuration of those resources can have implications for the type of flexibility that large loads may be able to offer, whether those are a number of hours per year, the duration of any individual response. So I think there's work to do, and I hope that we can get there, because I think this will really be able to really enhance planning and move from a place where we're making this kind of maybe unrealistic assumption of fully firm to one that is more dynamic and adaptable and can really tap into and value the role for flexibility, creating incentives for accelerated interconnection that benefit utilities, that benefit large loads, and ultimately benefit all customers. So I want to thank you for your time, and looking forward to your questions.
Yeah, thank you, Aaron. That was really fascinating. As you, we did have a question in the chat, but they said never mind. So I was actually curious, as you are thinking about this, what do you think the biggest challenge is in front of like commission staff and commissioners as they think about how utilities are doing this?
Yeah, I mean, I think there's a lot of challenges, as was clear from the presentation. The biggest challenge, um, I I think it's, really that last slide. I think making sure that we can get the data that we need, given the high degrees of uncertainty, uh, given the fact that, unlike traditional loads or generator performance, there just isn't as much of a historical record for the data. Um, as well as I think just being able to work effectively with large loads, with data centers in order to get that. I think that is really key to unlocking the type of robust, empirical analysis that can give us confidence on how and how flexibility might show up, what it might look like. Fortunately, I think that's something that is solvable. We just need to start laying the foundation.
Okay, thank you. James.
Thanks, Deborah. And I'm glad you asked that question, Deborah, and highlighted what Heather asked, because I think it's a callback to the question she asked for Jeff about data and that being a really big deal for the planners and certainly for the operators eventually, right? And how much they can count on these resources. With a few minutes left here, Aaron, maybe a clarification, and I think Jeff maybe touched on it. When we're talking about large loads providing flexibility, uh, what are we thinking is the most um, appropriate scenario to think about and where they can provide the most value? Is this a couple hours a year? Is it just at emergency periods, right, when things are especially tight? Is it kind of more regularly throughout the course of the year? When we're talking about the value of this flexibility, where do you think that lies?
Yeah, I think specifically for the types of resource adequacy applications that can allow us to avoid the need for new infrastructure, that's really at these sort of peak load, uh, low operating margin uh, scenarios that are showing up, in the like RA analysis, in the sort of loss of load or loss of load adjacent hours that are really quite infrequent overall. Our systems are designed to, what broadly speaking, designed to this 1 day in 10-year loss of load expectation standard. And so I think it really is a fairly small number of hours that is driving that sort of incremental loss of load risk. Um, I do think it's an interesting question, though, of, well, what if we think beyond that? And are there other opportunities to provision flexibility services that maybe span beyond that? I think as far as like the accelerated interconnection and avoiding the need for new capacity, that's maybe not as relevant. But as far as additional revenue streams, additional value that these can provide as sort of grid-facing resources, I think that could be an interesting question to explore.
All right, thank you so much, Aaron. Thank you for the presentation. Really engaging, good information. Thank you. All right, and if people have more questions for Aaron or any of the other speakers, again, their information is available at the end of their presentations, which we shall be sharing, NARUC shall be sharing. All right, let's turn it over to our last presenter, Elaine Hart, and you'll talk about the Northwest. Thank you.
Hey there, can you hear me okay?
Yes, we can.
Okay, let me make sure that my slides are good here. How's this?
There we go. Perfect.
Oh, you got it? Okay, great. Thanks so much for having me today. That was I really appreciated that last presentation in particular. I think it was a great setup for what I'm going to talk about as well, and described a lot of the motivation and reasoning behind the way that we approach this problem. So I'm going to be talking through what we're calling it's a review of another study that was conducted this last year. The work that we did was to sort of like review this study that E3 had conducted examining resource adequacy in the Northwest. That study is still underway, but they released phase 1 in October, and it raised a lot of eyebrows in the region. And so we were hired by Grid Lab to sort of give an independent look to the study and its methodology, and to learn what we could about what E3 had found, corroborate it, find something different. Sort of just the scope was sort of open-ended, just see what we could see. We're a boutique consulting firm based in Portland, Oregon. We do a lot of work in integrated resource planning, capacity expansion, production cost modeling, and resource adequacy. And Grid Lab is a nonprofit organization that hopefully a lot of you are familiar with. So this study that E3 released phase 1 of in the fall, it found basically that the Pacific Northwest is facing a shortfall of about 9 gigawatts by 2030, which is a short 4 years from now. And this is a region where we do not historically have a great reputation for bringing a lot of capacity online. So this was pretty startling. I think a lot of people sort of hit the panic button when they saw the study. But a lot of people also scratch their heads because it's this seemingly sort of this very, very large need sort of came out of nowhere, and we're wondering what's driving it. I want to, before I jump into everything that we did, just shout out to E3 for being very open, answering all of our questions, and the study sponsors as well, as we were digging into what they were doing while they were still wrapping up phase 2. So they were very gracious and really appreciate their cooperation. We looked at 4 areas where we thought that it'd be helpful to have either more transparency or rigor. The first was large load flexibility, which I think is why I was invited to talk to y'all today. We also looked at hydro flexibility, imports and coordination with California, and retirements and conversions. The big headline was that large load flexibility appears to be, large load growth and large load flexibility appear to be the 2 big things that the future capacity needs in the region are going to hinge on. I will note, I'm going to get in a little bit into the hydro modeling as well. And I'm not going to get much into the imports and coordination with California, except that I do want to go back to this discussion about the RA contributions of transmission, because what we found was during winter events in the Pacific Northwest, the import capability is transmission limited. So there's a whole bunch of natural gas plants sitting around, not doing much of anything in the winter in California. That would be available, but we hit south to north flow limit. So this is another case where transmission is binding and is going to be important to consider as we think about regional solutions. But most of what I'm going to show you today is about large load flexibility. So, we had just a couple of months to do this study. And E3 had started off with a really wide-ranging sort of probabilistic analysis. So we did something that you don't often do in an RA analysis, which is we didn't look at a probabilistic study. We didn't look at all of the different weather and hydro conditions that you could encounter and understand the likelihood of encountering all of these events, E3 already did that. Instead, what we did was we zoomed in on a specific event that aligned with the types of events that their study flagged as particularly challenging for the region. What their study found was basically when we hit a cold snap in the winter and we have low hydro, we're going to run into those problems. And the problems could be very long in duration, multiple days. It's an energy constraint in these circumstances, not a capacity constraint. So it's a little bit different from some of the results maybe you've seen in Southwest or California about the value of data center flexibility, but we'll get into that. So what we did is we looked at a recent event that had the same types of conditions that E3 flagged as particularly problematic, which in the Northwest, folks around here will remember the January 2024 winter event where we had a cold snap, we had low hydro, the gas system was constrained, we had a few EEAs, the lights stayed on, but just barely. And so what we did was we tried to basically recreate that event in a production cost model, tune it and calibrate it to what actually occurred during that event, and then fast forward to 2030 and say, what if that event were to happen again? What if we experienced the same weather conditions, the same hydro conditions, but instead we're looking at the loads and the resource fleet that we expect to have in 2030? What's that same event going to look like? And then we started layering in solutions to see what they could contribute. So this is sort of a focus on a stress event. I wouldn't say you should replace probabilistic resource analysis with this, but we found that it's been a really valuable communication tool to take a real event that people understand and have some tangible understanding of, to communicate the needs. And also by focusing in on one event, we're able to test more things and also have a little bit more modeling rigor. I'm not going to walk through all of our assumptions and all of E3's assumptions, except that they're broadly aligned where they could be. There are two places where our methodologies were pretty different. One is that our modeling was optimization based. So that had an impact on what the hydro was able to do, and in particular, what the hydro was able to see. The hydro scheduling could see, for example, that these portfolios have more battery storage. And we found that the hydro energy storage co-optimization, there was a really interesting story about that I will get into if we have time here today. And the other thing that sort of other differentiation between the two approaches is that because ours was an optimization-based approach, we could actually have a zonal model with optimized transmission flows, which meant that we could capture transmission constraints. We didn't use a lot of granularity there, but it is a benefit of using an optimization-based model. And I'll let you read all of this on your own time. So it's not all that interesting. Okay, because we zoomed in on this one event, we wanted to validate the approach and see, if we just look at this one event, do we see capacity shortages and problems that are similar to what E3 identified as like the crucial RA problem under these scenarios? So we tried to recreate their loads and their assumptions and see what's the capacity shortage just during this month-long event. Well, it's probably about a 2-week event, kind of right in the middle of the month. What's the shortage look like? And what we basically found was that event served as a really good proxy for the capacity needs that they identified when they tuned to the 1-day and 10-year standard. So this gave us some confidence that by testing variations on that event, we were going to get some insights that were at least like consistent with what they were finding. It also corroborated their findings. We basically found, yes, the region could face, if we see the loads that are in the load forecast that they modeled with the resource stack that we think we'll have in that year, we could be looking at a problem. So I think that gave us a lot of confidence, both in our approach and in their approach as well. It's always good to get the same answer with two very different methodologies. From there, we wanted to look at load uncertainty. So we tried to estimate kind of their load forecast based on information that they provided, and then we developed 4 high-level alternative load scenarios. The things that we toggled to develop these scenarios were, how fast are loads growing sort of organically, including things like electrification, and what is the forecasted data center demand. What we found in looking at their load forecast was they actually had not a whole lot of data center demand compared to some of the other forecasts for the region, but a lot of electrification. If the states in the Northwest meet their electrification goals, load is going to grow pretty fast. What we found elsewhere, and maybe forecasts that don't hit the policy goals but are more based on sort of like market adoption of these technologies, is probably less organic load growth, but probably more data center demand. And so we've just sort of mixed and matched those two sort of scenarios to create this range of future load conditions. All of our forecasts were, contemplating load growth that exceeds what we've seen in the recent past. So these are all like load growth, scenarios with some amount of growth. It's just, is it growing a little bit faster than it has over the last 5 years, or a lot faster than the last 5 years? Okay, I'm going to walk through our high-level findings. I'm going to dig in to some areas I hope you find that are interesting as we go. This plot shows the perfect capacity needs that we identified across the January 2024 conditions for our four load scenarios on the bottom here: baseline, low tech, low electrification, low growth. And then the top two, the very top one is what's reported in the E3 study. And then the pink bar there is what we approximated then the capacity needs would be if we put their load forecast into our model. So we're hoping that the pink and the dark pink and the light pink are sort of similar. That gives us some confidence. And the total bar is if loads grow, we have no ability to flex the data centers. They just show up and we have to meet them. And we don't have any sort of incremental resources from what we have today, and all of the retirements that are scheduled to happen all happen. So the full bar here is sort of like as bad as it can be. And then we sort of from there layered in solutions. The first thing we did was we added resources that are already in development. So you can see go from that like white shaded area is the capacity contribution during this event of all the resources that are kind of already coming down the pike that we expect to be online by 2030. These aren't planned. These are things that are like under construction. They're going to happen. While we were doing the study, there was an announcement that Centralia 2, rather than retiring, was going to be converted to gas. So we layered that guy in. And then the diagonal hashes here are the effects of introducing large load flexibility. And this ended up being sort of the big solution that we identified as crucial in the near term to mitigate sort of the worst consequences of potential supply shortages. So here, depending on the load scenario, we go from what in the press was a 9 gigawatt problem to, if we can implement large load flexibility, somewhere between a 0 to 3 gigawatt problem. So what do we do to meet that 0 to 3 gigawatt problem? We also want to take a look at, okay, there's a bunch of resources that are at various stages of development. They don't have, they don't have shovels in the ground yet, but they're going through the regulatory process. What happens if we allow these resources to enter the portfolio? What if we can get them online by 2030? We did all this modeling in a tool called GridPath. It's open source. You can find it on our website or on GitHub. And one of the kind of fun things about GridPath is it's really easy to change up the sort of structure of the model. So we had its production cost model, but it's very easy to add in investment variables. So we took that month and we said, okay, here are a bunch of resources that are could come online by 2030. Here are some high level costs for them. Select the resources that best meet the need to avoid loss of load events during that particular event. And the graph on the left here shows what was selected in one of the runs. So everything in the solid bar here, it was already in development. That was included in the initial runs, so the runs that we did. And then anything in that's light was selected by the optimization model. And there are a couple of like really interesting things that we saw when we allowed the model to select resources to meet the need. The first was if we allowed large load flexibility, the model would select batteries to meet the remaining need. This was totally unexpected. In the Pacific Northwest, we kind of have this narrative, especially because these are like long duration energy shortage events, that the value of short duration batteries is very low. And so when the model selected batteries, we sort of scratched our heads and kind of think, okay, why would it select batteries? And it turns out in this circumstance that if you have large load flexibility, you can solve the long duration energy shortage problem with large load curtailments. And the remaining problem, the problem that's being driven by not the large loads, but just organic load growth, can largely be met with short duration solutions. So large load curtailment, what we're actually seeing is the large load, the introduction of large loads is changing the nature of the problem. It's creating this energy problem. And if it solves itself through large load flexibility, you can sort of isolate that problem with the large loads, and the remaining problem is a short duration problem that's a lot easier to solve. You can even solve with batteries, which we found to be really surprising. We don't always find this answer if we don't allow the hydro and the batteries to co-optimize. And I'll talk about that on the next slide. But before I do, the last thing I want to say is that the we wanted to understand also, like, how do we can we avoid these large load curtailments? We have 19 gigawatts of resources that are in some stage of development in our data set. And what we basically found was even if we built all of them, we would still see these very long duration outages among the large load customers during the most constrained events. And we put large load curtailment in here as a very last resort. It's, it only happens if the alternative is for all customers, to be affected by a loss of load event. So these clean resources that are kind of in the queue in the Pacific Northwest are pretty well suited to meeting the organic load growth under most of the scenarios, but they're not even close to meeting the reliability challenge of serving these large loads during these critical weather events. One quick note on hydro storage optimization. This is something we're going to probably put some more work out there in the coming months on, because it was really interesting, and it's a point of departure between what we found and what E3 found. We actually saw pretty high ELCCs for 4-hour storage, as I kind of alluded to on the prior slide. And it was because the hydro was able to sort of shift energy between weeks, and it would actually use the energy storage to meet loads in prior days so that it could save up water for these very hard days. And it was kind of a new phenomenon that I hadn't seen before. We did some sensitivities here to see what's driving these high ELCCs. We still did find that the ELCC saturates, but saturates like much further out than E3 found. And we basically found that you need to account for interweek flexibility for hydro, that you can push water between weeks, which you can to some extent. And you needed the hydro optimization to see that the batteries were there so that they could make use of them. So these are two things I hope we see more of in future RA analyses. All right, I already kind of gave you these high-level findings. This is another way of looking at this question of like the management of the large loads. This graph on the right, I understand, is confusing, and in the deck that we put out there, I spend several slides sort of walking you through what all of these things mean. But what I want you to look at are those yellow areas. So the yellow areas for each of these scenarios is the range of curtailment durations of large load that's needed to avoid unserved energy for other customers. And the amount of curtailment, the duration of curtailment, depends on how many resources, clean resources, are added to the portfolio. So across almost all of the portfolios, you can, meet organic load growth with just a little bit more than the resources that are already under development. You can avoid that red bar there just by moving that vertical gray bar a little bit to the right for that baseline and low tech scenario. And it's already enough resources to avoid unserved energy for low electrification and low load growth. But you can't really avoid large load curtailments, even if you were to build out all of that 19 gigawatts of stuff that I mentioned on the last slide. So we're looking at curtailments between 50 and upwards of 200 hours. These are very long duration curtailments. They're not like what you would see in Nevada. They're not like the types of curtailments I think that people are thinking about now, where they can use battery backup and solar and storage and things like that. These are big energy problems. And I think what it means is that if you've got some sort of like critical computing that you need to be able to do, you probably don't want to send that to a data center in the Pacific Northwest during the winter. We probably want to leverage some of that geographic flexibility that was mentioned earlier in this training. And then the last thing I'm going to note is if you look at the very top in this slide list, if you look at the very top bar there, that's our approximation of E3's load forecast. This load forecast has fewer data centers, so less large load flexibility, but it has a lot more electrification. And we basically find that even if you build all of the proposed resources in the queue, you cannot avoid unserved energy under that scenario, because electrification has created a very challenging problem. Is that electrification forecast realistic? Probably not, but what it tells us is eventually we're going to be in a situation where it's very hard to meet even organic load growth. So to the extent that we can be thinking about solutions now, all the better. Another thing that we did was we looked at what this curtailment could look like from a customer perspective in terms of duration. So we took sort of two cases, one where we required loss of load to occur equally across all customers, large loads, existing customers, everybody, in a scenario that was short. In this scenario, it was the baseline scenario. It assumes resources and development come online, but it's just a little bit short. And in this case, because this is such a long duration energy event, like energy constrained event, you would see every customer would have to be curtailed on average about 19 hours. So this is catastrophic. This is much worse than Winter Storm Uri. This is catastrophic to customers in the Pacific Northwest. If you're allowed to curtail the large loads first, say, hey, we're an emergency. Sorry, guys, you got to go first, just for the sake of public safety and health and safety of our customers. You can get that average curtailment down to less than an hour for existing customers, but the large loads would have to be down for about 10 days. So this is a pretty stark picture of what this could actually look like for customers. And I think it's another way that I think it'd be useful when we're talking about resource adequacy. Sometimes it's hard to think tangibly about what it means to have a shortage. You can pretty easily convert it into average customer hours of outages, assuming that like everybody's going through this rolling brownout, and it gives you a better sense of like the consequences of these types of shortages and strategies to solve them. All right, I already said this, but in the end, it's really not a question of if, but when. We have a whole bunch of opportunities that we identified. The first biggest one was just considering policies that either require large load flexibility or emergency curtailment prior to curtailing other customers, just to sort of avoid those most catastrophic health and safety consequences. And then there's a bunch of other stuff here about transmission and coal to gas conversions, and please take a look if you have time. And the last thing, I want to end on an optimistic note here because I think it can get really scary pretty fast when we're talking about resource adequacy and these rapidly growing loads and how slow it is to bring generation on right now. I want to sort of remind folks that these types of like flexibility requirements, you might think of them as regulatory sticks, but they could also be an opportunity to drive innovation. These customers are fundamentally different than the customers that we're used to serving in this industry. We talk a lot about building a grid that is bigger than the weather. These customers are bigger than the grid and bigger than the weather. And they have flexibility and they have technology that could solve a lot of these problems, or they have deep enough pockets to buy down the cost curve of new technologies that are going to solve these problems. So what we found in the Pacific Northwest is if the right sticks are developed for these customers, they're going to face the most challenging resource adequacy problems first. Those resource adequacy problems are going to be faced by everyone eventually. And there's a lot of value in incentivizing them to help sort of society solve those problems. With that, I'll wrap up and take any questions.
Thanks so much, Elaine. That was really, really good. Not just because I'm actually in the Northwest either. I want to kind of ask you the same question because there aren't any in the chat, but what do you think the biggest challenge is for regulators, and what should they be paying the most attention to?
I think the biggest challenge is that this industry is evolving so quickly that it's not just hard to forecast what they're going to do, but it's hard to understand what they and have visibility into what's really needed versus what's a would be nice. Some of these data centers are critical infrastructure. Some of them are not. And I don't think we have the tools to understand and differentiate and develop regulatory policies that prioritize electricity service to those most, we differentiate, critical infrastructure does get special treatment and medically sensitive customers do get special treatment. We don't really know how to differentiate between these types of customers. person. I think that's really hard. And so I think people are maybe apprehensive to build sticks that are a little bit too strong, out of worry that we're going to undermine something that's really like a really important development in our economy and in our world. And I think we just need more information.
Thank you. So there is a question in the chat, and I actually want to open this up to any of the speakers to answer. So we talked several times about flexible interconnection policies today. Do you think those would be in commission interconnection standards, in IRPs, or rate tariffs, or all three?
Flexible interconnection.
Uh-huh.
But it probably depends on the jurisdiction.
Certainly.
Yeah. Although I'm not sure I would see it in an IRP. I'm an IRP person. I'd be surprised to see it in an IRP, so I'd maybe look to the tariffs. And I would invite others to join in this who probably work in other jurisdictions.
I think it's interconnection standards myself, but of course those actually do sort of turn out to be tariffs anyway. They're just not the rate tariffs.
Right.
So
Exactly.
yeah.
We're actually thinking in the summer at the ESIG summer meeting, we will have a whole day looking at flexible interconnections for large loads and everything from what we can learn from generator flexible interconnections. What does planning for this look like? What does it look like in operations? And then what does the tariffs and regulatory structure look like? So we're going to do a deep dive into this. And the reason we're covering all those areas because we think it will show up in all those, right? In the interconnection processes, in how you plan for transmission, in how you plan for RA, definitely in operations. What does your market participation model look like for these once they have flexible interconnections? So yeah, we're going to cover all that because we think it touches all those areas.
Yeah. One
Yeah.
last question, given what Sylvan and Varus have presented, how feasible is it currently for data centers to not need grid power for multiple days? Is it, and is it a 100, so the other question I had there is, it a 100% curtailment, or is it like a 50%, right? Which is
I
very
can
different.
say, yeah, I can say that what we did was we modeled these loads as lumpy and said they're going to get a phone call, and the phone call is going to say like we need you to cut pretty much everything for the next at least 24 hours, and then we were able to see how many of them would get that call basically over time. That's this graph here on the bottom, and the top line is the total. So you see during this event, there are multiple days where all of them that are being modeled have gotten the call and they're out for the day. It's pretty dire, and I don't think that we'll end up in this world. I think that if we're really that constrained, those at least customers who need really good uptime during the winter, they're just not going to build here. Go somewhere with a more mild climate. Go somewhere in the Southwest if you want to run stuff in the winter. And then we can run things in the summer here where maybe things are constrained in the Southwest.
Thank you. James, back to you.
All right, I think we are at the end of our 2.5 hour marathon. Thank you so much for everyone who joined the call, and a very big thank you to our speakers for that really engaging set of presentations. I'm hoping that everyone on the call has learned as much as I have, of everything from what Kevin did, Armando, then tag teaming on the transmission piece, and then the large load flexibility issue, the need and the opportunity that the last three presenters covered. So thank you so much to our fabulous presenters and to our audience for the good questions. As a reminder, and maybe Deborah, you're going to cover this, the next set of trainings. I can go over that, or I can pass it back to you to talk through that.
No, go right ahead. Thank you.
All right, perfect. Thank you. This again was the first in a series of 3 trainings. The next one will be April 16th, looking at forecasting large loads and harnessing flexibility. And that's really looking at resource and transmission planning. And April 30th, we will have processing large load interconnection requests. So we hope that you are able to join us for that. We have a good slate of speakers for those conversations as well. Again, thank you so much. Thank you, Neruk, for allowing us to bring our friends and colleagues to have this discussion. Any last words from you, Deborah?
No, I was trying to drop the link into the chat for the registrations, but it was not successful. If anyone is interested in registering and you have not yet done so, you're welcome to send me an email at dreynoldS@naruc.org. And again, it was a delight to have everyone here. Great questions, great presentations. Thank you so much. Oh, thank you, James. Perfect. All right.